So we're just one universe that nucleated out of this eternally expanding inflationary background to the multiverse of other bubbles, other universes that are out there now. And trying to test this, well, we can test inflation. At least we can test the simplest versions of inflation and find that they pass. It's true that you can cook up more and more complicated, super complicated versions of inflation that won't satisfy the observations that we see. But given how successful Occam's razor has been, assuming simplicity first, how fruitful that's been in latching onto experimentally verifiable ideas about how the universe really is, given how successful that's been, you got to be impressed with the fact that inflation predicts, we're going to show it I think in a minute, the spectrum of fluctuations of density in the universe so beautifully and so perfectly, and on data that is now extremely accurate. You can't even see the error bars on the spectrum of fluctuations, the power spectrum so-called, of the fluctuations that define the density and homogeneities in the universe. And it fits perfectly, I mean perfectly, with inflation. So I think inflation probably really happened. Okay? So that solves the puzzle of why we live in a living universe. It's exactly why we find ourselves on a living planet. How on earth could we find ourselves living on the only planet that we know of that is good for life? Well, framing it that way makes it sound like, something it's not. It's like obvious. We're self-selected. Of course we're going to be on a living planet. We're alive. Of course we're in a living universe. We live in a universe that is alive, and all the other universes out there that aren't alive, we're not going to be finding ourselves in those. So the nice thing is that no matter how many other universes in the multiverse there are that are terrible, that recollapsed into black holes immediately, or they just eternally inflated so that nothing ever got together. No atoms even found neighbors to be molecules with. Maybe there aren't even any atoms. There's just nothing but ultimate simplicity that's still expanding horribly. There's nobody in those universes to complain about how terrible their universe is. Okay? Most universes would likely come out of the cosmic oven botched. At least if you're a living organism and are rooting for a good universe. But there's nobody in them to complain. So of course we don't have to feel lucky. So there's our solution to why we live in a living universe. Just restating it all again right here. Alright, let's just look at one key parameter, the cosmological constant. This is a term that Einstein put into his equations, and it's a term, frankly, that deserves to be there. His equations of general relativity are differential equations, and they can remain true even with a constant thrown in, because the physical interpretation of having a cosmological constant in those equations is that there is an accelerating expansion tendency to empty space itself. It says that there is an energy density to empty space still. It's not like the inflation. Well, it's kind of like inflation, but now at a hugely more tiny level. The most natural expected value for the cosmological constant is more like, maybe I'm speculating here, but more like what the real inflationary number is, something about 10 to be 120 times, that's 1 with 120 zeros after it, times bigger than the one we actually have. So then you might say, well, gee, what are the odds of all the different values for this that we could have had that we would have ended up with one that was so incredibly tiny but yet not zero? See, we had assumed, even Einstein had assumed that it's really just zero. I mean, once he discovered that the universe of galaxies that we actually live in is expanding, then we didn't really need this to counter gravity. You just kind of have to go back and say, well, whatever it is that caused the Big Bang also got us our 14 billion years, and so there's no need for a lambda here. Well, what's interesting is that it doesn't have to be zero. It just has to be small. And if it just has to be small, why should it be exactly zero? Now that's starting to seem like a very, very special number. If the numbers that tumble out, okay, here's a point I didn't get across yet, but I should have. So if the universe in the largest context, the inflation context, is governed by the uncertainty principle, and none of the values that we now think of as being the values that describe the standard model were yet definable. They had not yet passed out of the quantum realm into a more classical realm where their values would be fixed. They could be basically anything. And it's exactly like, you know, in Casablanca with the roulette wheel, and the ball goes round and round and round, and you know, that's like the universe before, when it's so young that all the parameters are really undefined. And then as it expands and cools and you exit the quantum realm, then that's like when the little roulette ball falls into one of the numbers, and now it's not any old number, it's one number. And so why would it have to be that the roulette wheel ball would fall exactly on zero? And then you think about it and say, gee, you know, there actually is no reason that I can think of why it has to be zero. All that's required for a living universe, and that's the only constraint we're going to put on the universe because we're here, all it has to be is just very tiny. And so while some might have reacted to, and I know the people who discovered the expanding, inflating universe were first, in the words of Brian Schmidt, horrified at their discovery. It actually turns out to be perfect. And nobody's horrified, not Brian Schmidt or anybody else, about the fact that it is what it is. It actually turns out to be just the perfect number. We love our lambda not being zero. And in fact, if you go further, you could even make a good argument, at least Perron et al. In 2015 have made a good argument that you need to have it non-zero. You need to expand things a little bit, because if you don't, then you get too many gamma ray bursts, and gamma ray bursts can be fatal from a long ways away. And you don't want those going off anywhere close to you, or they sterilize your life-giving planets. So if you do a Bayesian probability distribution of what should we expect would be the most likely value for this, they describe it a little differently here, but this the density of the cosmological constant, and zero is actually like infinitely far this way. It's like 10 to the minus infinity. But they find that really there is a natural maximum to the probability distribution that's about 10 to the minus 123. And that's about right where it is. So, again, I find stuff like this really enchanting. Wow, it looks like we don't need a grand designer, that merely doing good Bayesian statistics, like all good astronomers will want to do these days, we can we can figure out that everything is pretty much just what we should have expected if we had just thought a little bit harder. So is the multiverse paradigm really true? Okay, we don't really know. I mean, again, proofs in a natural context are often very difficult because you're really saying this is proved. There is no other idea ever that anybody will ever think of that could possibly explain everything as beautifully as this one. It's kind of a big statement. But I tell you, it looks pretty compelling. So let's see. Let's go on to the next slide. That's not the slide we want. Again, what I did is I made one version of this big lecture, and I had it end in two different places, one for Astro 4 and one for Astro 3. So now we're going to go into new material, and we're going to just take for granted, okay, well, I can understand why we live in a nice universe. But now what we really want to know is, how can we find E.T.? We want to meet E.T. Now, you could ask the two different political parties and you might get different answers as to why we want to meet E.T. Maybe one party would say, because he's probably living on a good planet and we want to take it over. We want to outcompete him. And the other political party might say, oh, but we probably have so much to learn from him, and maybe they could even help us get over frankly, our maturity problems now that we're adolescents in the living universe, and we're not sure we're going to make it out of adolescence without committing suicide. You can ponder that. Okay, first question. How would we contact them? Or how would they contact us? So electromagnetic radiation is the fastest and by far the cheapest way to go. So if they are at all thinking about trying to communicate with us the fastest and also with the less cost, then you would be expecting them to be sending out signals somewhere in the electromagnetic spectrum. And, it seems pretty natural. If we're going to search for ET, why don't we start there? Should we look in gamma rays? Maybe they're trying to contact us using gamma rays, or X-rays, or ultraviolet, or visible, or infrared, or microwave, or radio. Well, gamma rays, X-rays, and ultraviolet are all too high energy. They'd ionize every atom, or almost every atom, that they hit, and thereby scramble any information encoded on those electromagnetic waves. So it would make no sense that they would try and encode some kind of, hi, how are you? Here we are, we're over here, and, how's it going? They would not try and encode that onto gamma rays, X-rays, or ultraviolet. What about visible light? Well, visible light doesn't have that problem. Only a few discrete wavelengths will get absorbed by the intergalactic or interstellar medium. But of course, you got another obvious problem. Visible light. I mean, just think about it. So you're now here on Earth, and you want to communicate with another civilization by visible light. So what are you going to do? You're going to go to Salinas Auto Mall and borrow their big garish lights that go off into the sky and then put Morse code on them or something and send them out to the stars? Well, you might think so, but realize that there's a competitor in visible light, and that's the sun. So you're going to outcompete the sun? Really? I don't think so. So that really doesn't make a lot of sense. Now you could give the same argument to infrared light, even though the sun is much dimmer in infrared light. But still, I mean, there's no way that on Earth you could generate as much infrared light to make a real go at competing with the sun. But it has been realized and even technologically achieved that if you concentrate your infrared beams, your infrared signals into a tiny enough amount of time, a picosecond, that during that tiny bit of time you actually can compete with the sun. You can compete with it decently. So maybe they would be sending us nanopulses of infrared. Maybe. We haven't really looked in infrared that way at this point. It would seem a lot easier, though, to communicate in radio. That's where we're going to go. But let's do one more band here. So what about microwaves? Would they try and compete with the cosmic microwave background? 99% of all the photons in the universe are cosmic microwave photons. 99%. They vastly outnumber the photons created by all the stars and all the galaxies in the universe. Cosmic microwave background, by the way, is generated by the Big Bang itself, and that radiation was freed when the universe cooled. As it expanded, cooled enough to make neutral hydrogen, and then neutral hydrogen will not interfere with those waves. Yeah, so this is sharp competition. You might think probably not. Radio is the most obvious way to go. It's dark in this band. If you had radio-equipped eyes and you went out on you went out on any night at all, dark or not, and you looked up, you'd see hardly anything. You might see a dim little blur where Jupiter is. Jupiter has some radio waves coming. You'd see a little blur where the Milky Way's core is. And that's about it. If you're looking in daylight, you'd see some fair amount of blur, I guess, from around the sun. Yeah, the sun and Jupiter and the center of the Milky Way is kind of most of what you got. Now, if you got really good radio antennas, of course, you can see a lot more. But basically, it's dark. It's dark in that band. So where would you look in this band? There is, after all, a lot of wavelengths there to choose from. So here's where astronomers have gotten kind of psychological, but also physical. So it turns out that the nice compromise, I should tell you, the whole radio band is not perfect. So again, if you go towards the short wavelength end, you're going to be getting more and more noise from the cosmic microwave background. And if you go too long a wavelength, then there's problems with penetrating through the Earth's atmosphere. And so there's kind of a sweet spot in the middle where it's quietest. It's at about 1420 megahertz. And coincidentally, that also happens to be where hydrogen and OH, its compadre, have their principal absorption bands. And H2O, add these two together, you get H2O, you get water. And we think water is essential for life. So even if they were just trying to read our minds about where would we think would be friendliest, maybe galactic civilizations congregate around the water hole in the electromagnetic spectrum. At least it's a Santa Cruz-y thought. So that's where SETI is focusing their attention, is sweeping through thousands and thousands of stars that might have life around them in this general area. So here you have noise from the microwave background, and here you have other noise that you want to avoid.